In this video, I will teach you about linear independence. Okay, so let's say here the set S, okay, include V1, V2 until Vn in a vector space V and are said to be linearly independent if we can write C1 multiplied with V1 plus C2 multiplied with V2 plus and so on plus Cn multiplied with Vn equal to 0 vector. Implies that all the scalars C1, C2 until Cn equal to 0. So, what is the 0 vector here? So, the 0 vector here is depend on the vector space V. So, for example here, if V here is vector space R3, so then the 0 vector will write in this form. Okay, 0, 0, 0. But let's say if V is the vector space polynomial of degree 2 or less, then the 0 vector will write in this form. 0 plus 0x plus 0x squared. Or you can write 0 vector equal to 0x squared plus 0x plus 0. And the third one, if let's say vector space here is matrix 2 by 2. So, then the 0 vector will be in this form. Okay, matrix 2 by 2 with all the element inside the matrix is 0, 0, 0, 0. The next thing you need to know is how to determine the linear independency of a set of vectors. So, we have two steps here. Okay, first, we formulate the linear combination. Okay, C1, V1 plus C2, V2 plus and so on plus Cn, Vn equal to 0 vector. Okay, and then the second one, okay, we solve this homogeneous system if all the constants are 0, means that C1, C2 until Cn equal to 0, means that we have trivial solution. Then the set S is linearly independent. So I will show it to you how to determine the linear independency of a set of vectors based on the example. Example 1. Determine whether the following vectors are linearly independent or not. So, we need to show that is V1, V2 and V3 here are linearly independent or not. So, the given vector here is in R3. So, how we solve or how we show the linear independency of these three vectors. So, the first step, we form a linear combination. Means that we write here C1 multiply with V1 plus C2 multiply with V2 plus C3 multiply with V3 equal to 0 vector. So, remember here, C1, C2 and C3 are constant. Next step, we substitute vectors V1, V2 and V3. So, we will have this one, C1 multiply with V1 plus C2 multiply with V2 plus C3 multiply with V3 equal to, okay, now the 0 vector here must be 0 vector in R3 based on the given vector in the question. The next step, we multiply C1 inside the bracket. You will have here C1, C1, negative C1. And then we multiply C2 here inside the vector V2 here. So you will have here C2, 0, negative C2. And then plus C3 here, we'll multiply with the vector V3. So you will have here 2C3, C3, C3 equal to 0 vector. So the 0 vector here is 0 vector in R3. Then we add these 3 vector here. So remember how to do the addition here. So the first element here C1 plus with the first element here C2 plus with the first element here 2C3. So you will have here C1 plus C2 plus 2C3. And then the second element here C1 plus 0 plus C3. So we will have this one. And the third element here negative C1 minus C2 plus C3 equal to 0 vector. Okay, then from the previous step here, okay, so we can come up with the system of linear equation. So how you do it? Alright, the first element on the left hand side equal with the first element on the right hand side. So that's why you will have here C1 plus C2 plus 2C3 equal to 0. The next one, the second element on the left hand side equal with the second element on the right hand side. So you will have here C1 plus C3 equal to 0. And the last one, the third element on the left hand side equal with the third element on the right hand side. So you will have here negative C1 minus C2 plus C3 equal to 0. Next step, we need to solve the above homogeneous system to find what is C1, C2 and C3. So I use the Gauss-Jordan elimination method to solve the system of linear equation above. So first we write the augmented matrix from the system of linear equation here. So I will have this one. And then please do it on your own. Okay, you reduce this augmented matrix until you get this matrix as your final augmented matrix. From the final augmented matrix, we can say that the solution is C1 equal to 0, C2 equal to 0, and C3 equal to 0. So when we get C1 0, C2 0, C3 0, means that our system here is trivial. So we can write it here as the solution is trivial since C1 equal to 0, C2 equal to 0, and C3 equal to 0. So we can conclude that the set S or the given set here, V1, V2, and V3 is linearly independent. Or there are another method you can use to determine the given set is linearly independent or not. So here another method to determine if the system of linear equation is trivial or non-trivial is to find the determinant of the coefficient matrix. Okay, so coefficient matrix here is A. So if A here is a square matrix, the system is trivial. If determinant of coefficient matrix or determinant of matrix A not equal to 0. Otherwise, it is non-trivial. Means that we find the determinant of the coefficient matrix, and then if the determinant not equal to 0, then we can conclude that the set is linearly independent. For the example 1, okay, from the system of linear equation, you can write as a matrix form. in this form. A multiply with X equal to B. So A here is the coefficient matrix. If you can see here, the coefficient matrix is a square matrix. Means that the size of this matrix is 3 by 3. So you can use determinant to determine the given vectors V1, V2 and V3 is linearly independent or not. So then we find the determinant of matrix A. So you can use the cofactor expansion. Let's say here I use the cofactor expansion along the second column. So the formula will be A12 multiply with C12 plus A22 multiply with C22 plus A32 multiply with 3C2. And then you formulate using the cofactor expansion, and finally you will get the determinant for matrix A is negative 3. So if you can see here, determinant of matrix A not equal to 0. So when the determinant of matrix A not equal to 0, we can directly conclude that the given set or the set S is linearly independent. Then you can write the conclusion here. Since the determinant of matrix A equal to negative 3, not equal to 0, therefore the set S is linearly independent. But please remember, we can only use the determinant of coefficient matrix if A or if the matrix A is a square matrix. Means that size of matrix A is n by n matrix. For example 1 just now, the vector space in R3. So we try to take a look at example 2 here. Okay, if we can see here, our vector space now in polynomial degree 2 or less. Okay, same thing. We need to show that the set S, set S here involve polynomial of degree 2 or less is linearly independent in P2. So the solution here will be, the first step, the same step as the previous example. We form a linear combination. So please write it as this one. C1 multiply with 1 minus x squared plus C2 multiply with x plus 2 plus C3 multiply with x power of 2 equal to 0 vector. So if you can see here, we have 3 vectors in polynomial of degree 2 or less. So that's why we have here C1 multiply with the first vector plus C2 multiply with the second vector plus C3 multiply with the third vector. Then equal with the 0 vector. Next, we multiply C1, C2 and C3 inside the bracket. So you will have this one. C1 minus C1x squared plus C2x plus 2C2 plus C3x squared. So now equal to 0 vector. So now 0 vector here must be in polynomial of degree 2 or less. So it will be in this form. 0 plus 0x plus 0x squared. Next step, we rearrange the equation on the left hand side. Alright, so you try to rearrange the term without x, term with x, and term with x squared. Alright, so the next step, we factorize. So for this one without x, so you will have here C1 plus 2C2. For x, we only have one term here, then you just write it back. C2 multiply with x. And for this one, we factorize x squared. So you will have here negative C1 plus C3 and then multiply with x squared equal to 0 plus 0x plus 0x squared. Then from this step, we can come up with the system of linear equation. So remember, for the polynomial, we compare the coefficient for x squared, for x, and without x. Remember the coefficient. So what we will get here? So the first one here, okay, without x. So you will have here C1 plus 2C2 equal to 0. And then the coefficient for x only, so C2 here equal to 0. So you will have for the second equation. And then the third equation here, you compare the coefficient for x squared. So here negative C1 plus C3, and this one equal to 0. So that's why you will have this system of linear equation. Then next step, we solve the above homogeneous system. Okay, so same thing, use the Gauss-Jordan elimination method to find what is C1, C2, and C3. So you write the augmented matrix. Alright, so you will have here 1, 2, 0, 1, 2, 0, 0, 1, 0, 0, 1, 0, and then this one negative 1, 0, 1. So negative 1, 0, 1. So this one, you write it B here. So the B here now is 0, 0, 0. So please do it on your own. You try to reduce this augmented matrix using the elementary row operation, and make sure you will get this final form here. And then from the final augmented matrix here, we can say that the solution is trivial, since C1 equal to 0, C2 equal to 0, and C3 equal to 0. Then you can conclude that therefore the set S, alright, the set S here given in the question is linearly independent. Or we can use another method by finding the determinant of matrix A. So from the system of linear equation, you can write as a matrix form, and then we can see that the matrix A here, the coefficient matrix A is a square matrix. So we find the determinant of A. Okay, using the cofactor expansion, you try to find on your own the determinant of A, and then you will get the determinant of A equal to 1. Okay, then you can conclude, since the determinant of A equal to 1, not equal to 0, therefore the set S is linearly independent. So remember again, if the coefficient matrix is a square matrix, then you can use the determinant to determine the set S or the given set in the question is linearly independent or not.